the threshold voltage, commonly abbreviated as VTH or VGS, of a field effect transistor is the minimum gate-to-source voltage differential that is needed to create a conducting path between the source and drain terminals. At gate-to-source voltages above the threshold voltage but still below saturation or VDS, the transistor is in its linear region, also known as ohmic mode, where it behaves like a voltage-controlled variable resistor. When referring to a junction field effect transistor, the threshold voltage is often called pinch-off voltage instead. This is somewhat confusing since pinch-off applied to insulated gate field effect transistor refers to the channel pinching that leads to current saturation behavior under high source drain bias, even though the current is never off. Unlike pinch-off, the term threshold voltage is unambiguous and refers to the same concept in any field effect transistor. Basic principles: in N-channel enhancement mode devices, a conductive channel does not exist naturally within the transistor, and a positive gate-to-source voltage is necessary to create one. The positive voltage attracts free floating electrons within the body towards the gate, forming a conductive channel. But first, enough electrons must be attracted near the gate to counter the dopant ions added to the body of the FET. This forms a region with no mobile carriers called a depletion region, and the voltage at which this occurs is the threshold voltage of the FET. Further gate-to-source voltage increase will attract even more electrons towards the gate which are able to create a conductive channel from source to drain. This process is called inversion. In contrast, N-channel depletion mode devices have a conductive channel naturally existing within the transistor. Accordingly, the term threshold voltage does not readily apply to turn such devices on, but is used instead to denote the voltage level at which the channel is wide enough to allow electrons to flow easily. This ease of flow threshold also applies to P-channel depletion mode devices, in which a positive voltage from gate to body source creates a depletion layer by forcing the positively charged holes away from the gate insulator semiconductor interface, leaving exposed a carrier-free region of a mobile, negatively charged acceptor ions. In wide planar transistors the threshold voltage is essentially independent of the drain source voltage and is therefore a well-defined characteristic, however it is less clear in modern nanometer-sized MOSFETs due to drain-induced barrier lowering. In the figures, the source and drain are labeled N+ to indicate heavily doped N regions. The depletion layer dopant is labeled NOR to indicate that the ions in the depletion layer are negatively charged and there are very few holes. In the bulk the number of holes per equals Na, making the bulk charge neutral. If the gate voltage is below the threshold voltage, the transistor is turned off and ideally there is no current from the drain to the source of the transistor. In fact, there is a current even for gate biases below the threshold current, although it is small and varies exponentially with gate bias. If the gate voltage is above the threshold voltage, the transistor is turned on, due to there being many electrons in the channel at the oxide-silicon interface, creating a low-resistance channel where charge can flow from drain to source. For voltages significantly above the threshold, this situation is called strong inversion. The channel is tapered when Vd greater than 0 because the voltage drop due to the current in the resistive channel reduces the oxide field supporting the channel as the drain is approached. Body effect. The body effect refers to the changes in the threshold voltage by the change in the source bulk voltage. Because the body influences the threshold voltage, it can be thought of as a second gate, and is sometimes referred to as the backgate. The body effect is sometimes called the backgate effect. For an enhancement mode, NMOS-MOSFET body effect upon threshold voltage is computed according to the Shishman-Hodges model using the following equation. Where is the threshold voltage when substrate bias is present, is the source to body substrate bias, is the surface potential, and is threshold voltage for zero substrate bias, is the body effect parameter, is oxide thickness, is oxide permittivity, is the permittivity of silicon, is a doping concentration, is the charge of an electron. Dependence on oxide thickness. In a given technology node, such as the 90 nanometer CMOS process, the threshold voltage depends on the choice of oxide and on oxide thickness. Using the body formulas above, is directly proportional to, and, which is the parameter for oxide thickness. Thus, the thinner the oxide thickness, the lower the threshold voltage. Although this may seem to be an improvement, it is not without cost. Because the thinner the oxide thickness, the higher the sub-threshold leakage current through the device will be. Consequently, the design specification for 90 nanometer gate oxide thickness was set at 1 nm to control the leakage current. This kind of tunneling, called Fowler-Northeim tunneling, where and are constants and is the electric field across the gate oxide. Before scaling the design features down to 90 nm, a dual oxide approach for creating the oxide thickness was a common solution to this issue. With a 90 nm process technology, a triple oxide approach has been adopted in some cases. One standard thin oxide is used for most transistors, another for I/O driver cells, and a third for memory and pass transistor cells. These differences are based purely on the characteristics of oxide thickness on threshold voltage of CMOS technologies. Dependence on temperature, as with the case of oxide thickness affecting threshold voltage, temperature has an effect on the threshold voltage of a CMOS device. Expanding on part of the equation in the body effect section. Whereas Boltzmann's constant, is temperature, is the charge of an electron, is a doping parameter and is the intrinsic doping parameter for the substrate. We see that the surface potential has a direct relationship with the temperature. Looking above, that while the threshold voltage does not have a direct relationship but is not independent of the effects. On average this variation is between a 4 megavolt per carat and a 2 megavolt per carat depending on doping level. For a change of 30 °C this results in significant variation from the 500 megavolt design parameter commonly used for the 90 nm technology node. Dependence on random dopant fluctuation, RDF, is a form of process variation resulting from variation in the implanted impurity concentration. In MOSFET transistors, RDF in the channel region can alter the transistor's properties, especially threshold voltage. In newer process technologies RDF has a larger effect because the total number of dopants is fewer. Research works are being carried out in order to suppress the dopant fluctuation which leads to the variation of threshold voltage between devices undergoing same manufacturing process. See also, MOSFET operation, channel length modulation, references. External links, online lecture on Threshold voltage and MOSFET capacitances by Dr. Lindstrom.